The first part of chapter 21 looks at writing out nuclear decay reactions for our 4 major decay types. So we're going to do the practice problems posted in the module. So the first one is writing out the decay. So we're looking at question 1, and A says that Einsteinium, so that's ES 252, and it says it's an alpha decay. We have Einsteinium 252 with an alpha decay. So we're going to look at the periodic table, look at Einsteinium, write out its isotope here. So if we look at a periodic table, and so we look at our periodic table, Einsteinium is right here. So ES Einsteinium, so we have 99 as the atomic number. So we're going to use that to build our isotope here. Okay, so we have 99 ES 252. Okay, so this tells us it's an alpha decay. So we know we have an alpha particle, and alpha particle is a 4,2-He. So we release an alpha particle, and then we have a new element that's produced in this reaction, in this nuclear reaction. Okay, so we have a nucleus with 252 particles. So if 4 of them are now in this helium atom, the difference between the two has to be the particles that are in our new atom. So 252 minus the 4 that are going in here leaves us 248 particles left. Okay, so if we have 99 protons, 2 of them are going into this helium. The difference between those, or 97, is how many protons are in our new element. So if we look at our periodic table, we're looking for the element with 97 protons, and that is here. That is berkelium, so BK. Okay, so thank you, periodic table. So our symbol here is BK. So this is our alpha decay. 2 protons, 2 neutrons lost to make our alpha particle, and our resulting particle here has 4 less for the mass number, and it has 2 less for the atomic number compared to the original atom. And then again, that's because of the particles that go into forming our alpha particle. Our 2 protons are 2 neutrons. Okay, so B tells us we have strontium 90, and it's undergoing a beta decay, so beta minus decay. So strontium 90 has a beta decay. Okay, so we look at the periodic table. Strontium is here. Strontium has 38 protons. So we have 90 SR, and we have 38. So we have a beta decay. Sorry, that's a minus. So we have a beta decay. So we know our particle that's emitted is a beta particle. So in equations, we represent it as 0 minus 1 E. So that's an electron or a beta particle that were produced here. Okay, so we're going to just balance the mass numbers and atomic numbers just like we did above. So if we have 90 particles in the nucleus and we're not changing that, we're not removing any particles in the nucleus, that means we still have 90 particles in the nucleus. So what we're doing here, we have 38 protons in the nucleus of an atom. In a beta decay, we're taking a neutron and we're turning it into a proton. So we are taking a neutron, turning it into a proton. So this 38 becomes a 39. But if we look, 39 plus minus 1 equals 38. But the physical process in the nucleus is we are gaining a proton because a neutron is being turned into a proton. And as a result, a beta particle is ejected. Okay, so let's look at our periodic table. Let's look for element number 39. So element 39 is yttrium. So that is Y. So we'll put our Y here. So here is the beta decay of strontium-90. Okay, so C says that iron, so Fe56 is the product. So it is the product of a positron decay, so of a beta plus decay. Okay, so we're going to do this one a little bit different. So this is the product. So we're going to write our arrow, and we know that this is 56 Fe, and iron has atomic number 26. And we know our second product is a positron, a beta plus, so 0, plus 1, and E. So we need to figure out what the original radioactive nucleus was. So we're just going to work backwards from what we did above, but the same rules apply. The sum of the mass numbers here has to equal the mass number here, and the atomic numbers, or the subscripts here, have to equal this up here. So 56 plus 0 gives us 56. Now we have 26 plus 1, which gives us 27. If we look on the periodic table, element number 27 is cobalt. So CO. So our original nucleus was cobalt 56. So looking at our mass number, since our mass numbers are the same, that means no protons and no neutrons were removed from the nucleus, right? But we did have 27 protons. Now we have 26 in the new atom. So what happens in a positron decay is we take a proton and we convert it into a neutron. So up here in this one, in this type of decay, we have a neutron that is turned into a proton and a beta particle. So that's why our atomic number went up 1. Over here, we have a proton being turned into a neutron and a positron. Okay, so plus. So if you look, kind of the charges balance here. We have a plus charge and a minus charge to give us our neutral neutron. Here we have a positive proton. If we're turning it into a neutron, we have to have a way to carry out the positive charge, and that is where the positron comes in. But again, we're not changing the total number of particles in the nucleus of the atom. That's why the mass numbers don't change. We're just turning a proton into a neutron or a neutron into a proton, depending on which type of decay we have. Okay, so the last one, part D. Part D says zinc 65. So zinc 65 decays through electron capture. Okay, so in this one, we have a proton in the nucleus of the atom that grabs an electron from the electron cloud of that particular atom, and we take an electron and a proton and essentially turn it into a neutron. Okay, so we have 65 zinc with atomic number of 30. So if it is grabbing an electron, it's reacting with an electron. So we put that on the reactant side. So again, this comes from the electron cloud of the atom. So this is one of zinc's electrons in its electron cloud. Okay, so zinc plus the electron. Okay, so we're not adding any new particles into the nucleus, so we still have 65. Again, 65 plus 0 is 65. If we look at the bottom, we have 30 plus a negative 1, which gives us 29, which gives us copper. Okay, so if we look at what happens in the electron capture, a proton in the nucleus grabs an electron from the electron cloud, and this is turned into a neutron. So essentially we're turning a proton into a neutron here, kind of similar to what we did here, turning a proton into a neutron. For this one, we eject the positron. This one, we grabbed an electron from the electron cloud. Proton and neutron together combined to form that neutron. So C and D kind of give us the same results, where the atom has the same mass number, but its atomic number has decreased by 1. So again, kind of get the same results here, slightly different way in which the reaction has happened. Okay, so here's our 4 essentially basic types of reactions. Okay, so our alpha, our beta, our positron, and our electron capture. Okay, so before I sort of conclude this video, I do want to look at kind of why those particular things occur. So I do want to look at here a zone of stability. So here is a plot of the zone of stability. So here we have protons on the x-axis, and here we have neutrons. So all of these here, this sort of zigzag line going through this sort of dark black, those are all stable isotopes. Okay, so when atoms are very, very small, the optimal ratio of protons to neutrons is 1:1. As the atom gets larger and larger, you need many more neutrons to make the atom stable. Okay, so we get much, much more. So when we're on this line right here, the nucleus is said to be stable, and we don't expect there to be any type of nuclear decay. Okay. So as we go above the zone of stability, you can see all of this above the zone is blue in color, and that is typical of a beta decay. So remember, in a beta decay, we're taking a neutron and turning it into a proton. So for above here, this means we have too many neutrons, or the number of neutrons in the atom is greater than what needs to be on that line. So if we take a neutron and turn it into a proton, we decrease the neutrons and we get closer to this zone of stability here. Okay, so below the zone of stability, see that's predominantly orange. Orange is beta plus. So if you look here, remember in a beta or a positron and electron capture, we turn a proton essentially into a neutron. So down here, it's like we don't have enough neutrons. So since we're below that line, our number of neutrons is too low. So we're taking a proton, turning it into a neutron to move up towards that zone of stability. So actually, also down here that's not shown is part of these positron decays are also electron captures. So there is some of that also. As we get up near the top, we see there's a lot of yellow. Okay, so as we move higher and higher and the atoms get larger and larger, it turns very yellow. Yellow is alpha decay. So alpha decay occurs when the atom is just extremely large. So when we have to just get rid of as many particles as possible in the nucleus to decrease its size, the typical mode of decay is alpha. That's not always true. You see there's some scattering of alpha in here. But for the most part, when atoms get very, very large, it starts to decay more through alpha decay. And also notice about atomic number down here, 82. So if you look up here at 82, our sort of black or stable nuclei, it kind of disappears after this. So pretty much after atomic number 82, if you look at our periodic table, that's lead. Pretty much everything larger than lead is radioactive. Every single isotope larger than lead is radioactive. And that's because the nucleus is too large to be stable. So there's too many electrostatic forces that are countering all those strong nuclear forces that would hold it together. So we kind of see our stable nuclei kind of disappear right there after lead. Okay, one last thing. Look at sort of a similar plot. Like, why are you showing me this? This looks exactly the same. I just want you to kind of note here that our stable nuclei are that zigzag line going down the middle. That's stable. All these other colors are unstable, but their sort of half-life gets increasingly short. Okay, so when we're in the warmer colors, we have nice longer half-lives. So that's really, really close to that zone of stability. As we move away from that zigzag line, they become much cooler in color, and the half-lives, or sort of how long that atom exists, becomes much, much shorter. So as we move away from the zone of stability, the particular isotope or the nucleus becomes much more unstable, and the time it takes it to decay becomes a lot shorter, or its half-life. So as we move away from that, its radioactivity increases and our half-lives get shorter.